All right, let's say we wanted to look at the average rate of change between 2 points on a graph, right? So here, let's say that this is a graph, right? And we have a function. Call this function f of x. And I want to just take 2 arbitrary points on this function. So let's say I have this point here. This is point x1, and its equivalent y value. I'm going to call this guy f of x1, okay? And let's take another point, say here. And this is point x2, and its equivalent y value f of x2. Okay, so using these 2 points, to find the average rate of change between the 2 points, you need to find the slope of a secant. Now, first off, what is a secant, right? So a secant is a line that extends between the 2 points, as shown here, right? And basically, because this is a line, the slope of the secant can be expressed as the rise over the run, basically, right? So it's y2 minus y1 over x2 minus x1, okay? So you might have seen this already in previous math courses. If you were looking at it on a functional perspective, you could also write y2 as f of x2 and y1 as f of x1. Okay, so both of these really mean the same thing. Just for simplicity's sake, I'm going to make one of these points 0.1, so I'm going to do -4, -1 is 0.1, and for 0.2 I'm going to use 2 and 6. These are the equivalent x and y values of each point, right? So this is x2 and this is y2, okay, so this should be a 6 here. And now what we can do is we can plug it into the formula. So the slope of the secant here is y2, which is basically 6 minus y1, -1, over x2, which is 2, minus x1, which is -4. So you get 7 over 6, right? So you gotta have to kind of work out the integers there. And yeah, this is your average rate of change. All right, let's say we wanted to figure out the average rate of change between 2 points on a particular function. In this case, I wanted to determine the average rate of change from x is equal to -3 to x is equal to 2. And our function in question here is f of x is equal to x minus 2x squared, right? So we know that the average rate of change is technically the slope of the secant. And from the previous video, we discussed that the slope of the secant is f of x2 minus f of x1 over x2 minus x1. This is equivalent to the y2 minus y1 over x2 minus x1 formula. It's basically rise over run. All right, so in this case, let's say that x2 is our endpoint, right? So I'm going to say x1 here is -3, and x2 here is 2, okay? So f of x2 is basically f of 2, which is equal to, if I plug in 2 into the function, you get 2 minus 2 times 2 squared, which is 2 minus 2 times 4, which will give you -6, all right? So what this is telling us is that f of 2 is equal to -6. In translation, what that reads out is y when x is equal to 2 is equal to -6. So the point here is 2 and -6. Okay, so that's one possible point on our graph. The other point, I'm going to use x1, f of -3 here. If I plug this into my function, I get -3 minus 2 times -3 squared. And basically you get -3 minus 2 times 9. Which is -3 minus 18, and that's -21. Okay, so f of -3 is equal to -21. All right. Now the equivalent point for this guy is -3 and -21. Okay, so now we have 2 points, right? We have 2 and -6, and we have -3 and -21. And I use the equation slope of the secant, and if I look at the slope of the secant, f of x2 is basically f of 2, right? So it's -6. So you get -6 minus f of x1, which we said was basically -3, this is x1, right, is basically -21. And this is over x2, which is 2, and it's basically mentioned here, and x1 here is -3, right? So you get, if you kind of do all these operations, you get -6 minus -21, right? So -6 plus 21, you get 15 over 2 minus 3, which is 5. So the slope of the secant is basically 3. Okay, so that's the slope of the secant. Alright, say we wanted to determine the instantaneous rate of change for the function f of x is equal to 4x squared minus 4 when x is equal to 4. Okay, now one way we can do this is through something called a small interval method. Okay. Now, first we need to kind of define what is a tangent, right? And what is the instantaneous rate of change. So let's say that our function kind of looks like this. And we're trying to figure out, the instantaneous rate of change at a single point, right? Now, instantaneous rate of change is going to only occur at a single point. It's not going to occur over an interval. That's the average rate of change. And when we're looking at the instantaneous rate of change, we're actually going to be looking at the slope that only touches that one point. Now, this line here is called a tangent. And the slope of the tangent is your instantaneous rate of change, right? Now, the problem here is finding the slope of tangent, really what calculus is all about, right? We're going to kind of investigate this later on, but there are multiple ways to do this, and I'm going to show you one of them. So it's called the small interval method, right? Technically, if you take an average rate of change, like a secant, right, and you shrink it smaller and smaller, and you make the interval close to 0, you eventually get to a tangent. Now, when we're looking at a small interval method, ideally we want to take a single point and we want to look at creating a small interval that encompasses that point. Now, usually when you're looking at this point, we can make a small interval using x plus minus 0.01. A more defined interval can be created by x plus minus 0.001. Okay, so this is how we can create a small interval. And when we create an interval, it's always between a lower limit and an upper limit, right? So I'm just going to kind of use this approximation, right? Because technically it'll give us really the same answer. If I use this approximation, and this is an approximation, if I use this approximation, the lower limit here is 4 minus 0.01, so that's going to give us something like 3.99, and let's call this the lower limit, and the upper limit here is 4 plus 0.01, which is going to give us a value like 4.01, right? So this is the upper limit. And technically our small interval is going to look like x is greater or equal to 3.99, but less than or equal to 4.01. Okay, so that is our small interval. And now when we have our small interval, at this small interval, the slope of the secant can actually be approximated as the slope of the tangent. So that's really the idea behind it. Now, if we're finding the slope of the secant, well, we know that the slope of the secant here is f of x2 minus f of x1 over x2 minus x1. Okay, so we'll just use the rise over run formula that we did in previous videos. And in this case, f of x2 here is, let's say x2 here is the upper limit, so let's say it's 4.01. So if I do f of 4.01 is basically 4 times 4.01 squared minus 4. Just going to calculate that out, and I get 60.32. Then I'm going to do f of 3.99, and I get 4 times 3.99 squared minus 4, right? Whoops. And if I punch that out, I get 59.68. And if I plug this into my function, right, f of x2, that's going to give me 60.32 minus f of x1 is 59.68. And divide this guy by x2, which is like 4.01, minus x1 here is 3.99. Okay, and if I calculate all this out, I end up with 32. Okay, and that is actually the slope of the tangent at that point. Alright, Tom and Jerry are learning new Japanese words together. The number of words Tom can remember after t hours is given by n is equal to 10t plus 100, while the number Jerry can remember after t hours is given by 5t squared plus 2. After the 5th hour, who remembers more words? At the 6th hour, who remembers more words? Who's learning faster? Explain your answer using instantaneous rate of change. So if we want to find the instantaneous rate of change, let's create a general function. Because of the fact that we're looking at two different time intervals, 5th hour, 6th hour. And the easiest way to do this is we're going to use the first principle method. And the first principle method involves the use of limits. F prime of x is equal to the limit as h approaches 0, f of x plus h minus f of x over h. Right, we can just memorize the use of limits. You don't need to understand limit properties in this course. Now, in this case, if we're looking at using the first principle, I'm going to do this for Tom. So for Tom, his function is n of t is equal to 10t plus 100. So if I'm using this equation, n prime of t is equal to the limit as h approaches 0, n of t plus h minus n of t over h. And your point here is to cancel out the h. N of t plus h here is equal to 10t plus h plus 100, which is 10t plus 10h plus 100. Okay. And if I look at the numerator, n of t plus h minus n of t is equal to 10t plus 10h plus 100 minus n of t in this case is basically 10t plus 100. You notice here that you get 10t plus 10h plus 100 minus 10t minus 100. So the 10t and the negative 10t cancel out, the positive 100 and negative 100 cancel out, and you're left with 10h. So this is the numerator, so n prime of t is equal to 10h over h, and then this is, I'm just going to make some space here, limit as h approaches 0, 10h over h, and then you can see that the h's cancel out, and this is equal to 10. Okay, so the rate of change for Tom is a constant 10 words per hour, right? Now if we're looking at Jerry, we'll do Jerry in blue. So Jerry's equation here is given by the equation n of t is equal to 5t squared plus 2. N is the number of words after t hours. And in this case, if you want to find the instantaneous rate of change, n prime of t here is limit as h approaches 0, n of t plus h minus n of t over h. So n of t plus h is equal to 5 t plus h squared plus 2, which is equal to 5t squared plus 2th plus h squared plus 2, which is 5t squared plus 10th, because you want to multiply it out, plus 10th plus 5h squared plus 2. And if you wanted to subtract this, n of t plus h minus n of t, this is basically equal to 5t squared plus 10th plus 5h squared plus 2 minus n of t, which is negative 5t squared minus 2. This and this guy cancel out, this and this guy cancel out, and you're left with 10th plus 5h squared for the numerator, right? So if you rewrite your limit here, your limit as h approaches 0, I'm gonna factor out an h here. You get 10t plus 5h over h cancels out. You let h equal 0, so you get 10t here. Okay, so this is basically for Jerry. N prime of t here is equal to 10t. Right? If we look at the 5th hour, and I'm just going to change up their variables here. But for Jerry, if we do n prime of 5 for the 5th hour, we get 50 words per hour. And if we look at Tom, we do n prime of 5, we should still get 10 words per hour. So he's reading at a constant rate of 10 words per hour. So Jerry is going to remember more words at the 5th hour, and for part B, I'm just gonna make some space here. Let's erase this portion. Right, for part B, for the 6th hour, we know that his reading speed is n prime of 6, which is 10 times 6. So he's going to do 60 words per hour now. So he's reading actually a lot faster, but Tom is still reading at 10 words an hour. Excuse me. So in the 6th hour, Jerry's still remembering more words. Right, Jerry's still remembering more words, and who's reading faster? Well, Jerry is reading faster because his rate of change, or his rate of change is increasing per hour, right? He's basically increasing his word count at least by 10 words in every hour, versus Tom is only reading at a constant rate of 10 words an hour. Okay, so Jerry is reading faster than Tom. Okay, so you can use rates of change to compare the speeds of two different things, basically. All right, let's estimate the slope of the tangent to the graph of the function y is equal to x to the power 4 plus 5x at x is equal to 2. So let's say that f of x here is equal to x to the power 4 plus 5x. I'm going to use the squeeze theorem, where I create a small interval in order to find the instantaneous rate of change, because we know that the slope of the tangent is the instantaneous rate of change, right? And if I create a small interval, I'm basically going to look at the point x is equal to 2, and I'm going to use x plus minus 0.01. So I can express x is equal to 2, I can express 2 as a value that's between 1.99 and 2.01, right? So the slope of the secant at this small interval will be equal to the slope of the tangent. So my instantaneous rate of change, or my slope of the tangent at x is equal to 2, is equal to f of 2.01 minus f of 1.99 over 2.01 minus 1.99. And the denominator here should be 0.02. Okay, and this is my instantaneous rate of change. Right, and then I'm going to solve for this. So f of 2.01 is equal to 2.01 to the power 4 plus 5 times 2.01. And if you crunch this out, okay, so this is going to give me 26.372. I'm going to use 4 decimals, so 3.3724. F of 1.99 is equal to 1.99 to the power 4 plus 5 times 1.99, and this is basically 1.99 to the power 4 plus 5 times 1.99 is equal to 25.6324. Okay, and then we plug this in to our expression. So the instantaneous rate of change is basically the slope of the secant of a very small interval, and this is basically the difference quotient. And we would do 26.3724 minus 25.6324 divided by 0.02. If I punch this out, 3724 minus 25.6324, divide this by 0.02, I got 37. Okay, so the instantaneous rate of change, or the slope of the tangent at the graph at x equal to is 37. Okay, let's take a look at another instantaneous rate of change question involving the squeeze theorem. So the number of boys B at the Comic Arts Festival after T hours is given by B is equal to T cubed plus 100T plus 1. Estimate the rate at which the number of boys is changing at the 4th hour. So if we're looking at determining the rate of change at the 4th hour, I'm going to create a small interval. So I'm going to let B represent a function of T. Is equal to T cubed plus 100T plus 1. And if you're looking at when T is equal to 4, a small interval for 4, you can use 3.99 and 4.01. Okay, So basically the slope of the secant at this very small interval will be equal to the slope of the tangent, which is equal to the instantaneous rate of change. So the instantaneous rate of change here is equal to b of 4.01. You can use the difference quotient at a small interval to figure out the instantaneous rate of change. B of 3.99 over 4.01 minus 3.99. And if you kind of simplify this, so b of 4.01 minus b of 3.99 over 0.02. So b of 4.01 is equal to, I'm going to plug this into my original function, so that's going to give me, so b of 4.01 is 466.48, 1, 2, I'm going to use 4 decimals, and b of 3.99 is equal to, b of 3.99 is equal to 463.5212, and then if I plug this in to find my instantaneous rate of change, this is going to give me 466.4812 minus 463.5212 divided by 0.02. So the instantaneous rate of change here is equal to 148. Okay, so there's basically going to be 148 boys per hour at the 4th hour. Okay, so that's what the instantaneous rate of change is.